All right, so welcome everyone to the second session of short talks at the Schubert seminar. Thank you for joining us. So today we have another three great talks, and we start first with Franquis Caraballo Alba from Florida State telling us about the Chern-Schwartz-MacPherson cycle of a matroid. Please take it away, Franquis.
Thank you. So for the rest of the talk, instead of saying Chern-Schwartz-MacPherson, I will just say CSM, but know that that's an abbreviation for that. And this talk is about joint work I did with Jeffery Liu, who's a fellow graduate student at Florida State. So the plan for the talk is that I will describe for you the CSM class of a scheme. Um, I will then give you a description of hyperplane arrangements in projective space and their combinatorics. Then we will generalize the relevant combinatorics to the concept of a matroid, and then we will see two different recipes for the CSM cycle of a matroid. Um, so the first thing we need to know is a CSM class of a scheme. We're going to be working over algebraically closed characteristic zero fields. And this is supposed to be a generalization of the total Chern class of a proper non-singular variety. For this, we need something that satisfies inclusion-exclusion, which we do by defining the functor of constructible functions. So it takes varieties and proper morphisms and spits out an abelian group and abelian group homomorphisms. Um, we define the group associated to a variety as the finite linear combinations with integer coefficients of indicator functions of closed subvarieties of the given variety. This is not important for the talk, but you can make this into a graded abelian group by deciding that the degree of an indicator function is the dimension of the corresponding closed subvariety. And we turn it into a functor by declaring the group homomorphism associated to a proper morphism F as the map that sends the indicator function of W to the function that, if you give me a point in the codomain of F, spits out the Euler characteristic of the intersection of W with the fiber of this map over that point. And there are two important theorems here. The first one by MacPherson is he showed that there's a unique natural transformation between the functor of constructible functions and the functor of Chow group that sends the indicator function of a proper non-singular subvariety, proper non-singular variety to its total Chern class. And then Kennedy in 1990 extended this result. The MacPherson result is only in the case where the field is the complex numbers. And then the result of Kennedy is the result for any algebraically closed characteristic zero field. Then, with this natural transformation, we define the CSM class. So if you give me a scheme that can be embedded into a proper non-singular variety, we define the CSM class of this scheme as the image under the natural transformation of the indicator function for that subscheme. And the guiding principle for the specific case of a choice of scheme that we're going to be using comes from a theorem by Alufi, which says that if you're talking about the complement of a simple normal crossings divisor, then there is a fairly short formula that tells you what the CSM class is. Something important here is that technically this is the Chern class of the bundle of differentials with logarithmic poles along the simple normal crossings divisor, but we won't be using that in the talk today either. So here is an example. I'm going to choose the union of two lines in P2. And we can decompose this union of two lines into both lines that form the union of the two lines and the point at which they intersect. If I want a function that is 1 along the union of the two lines, I can write that as the function that is 1 on the first line, the function that is 1 on the second line, and then I need to subtract the function that is 1 at the point they share. Using then the fact that these are P1s and points embedded in projected into in P2. We can compute directly what the CSM class is. And then if we wanted to compute the CSM class of the complement, we can also use the fact that P2 is proper non-singular and compute directly the CSM class for P2, subtract the CSM class for X, and we get a class that matches what Alofi's theorem tells us it should be. So what scheme am I picking that will hopefully give us something that is the complement of a simple normal crossings divisor? Hyperplane arrangements. So if you give me an r-dimensional vector subspace of Kn, we can define a hyperplane arrangement associated to this vector space choice by intersecting the coordinate hyperplanes in Kn with your choice of vector space and then projectivizing. So here's a specific example. This is the example I will be using, and we can even write down the equations for the corresponding hyperplanes or lines in this case. Something important to note, and very obvious immediately, is that this is not simple normal crossings. However, in 1996, De Concini and Procesi introduced this idea of wonderful models for the complement of a hyperplane arrangement, which is formed by blowing up the geometric flats of the hyperplane arrangement. So you start with points, then you look at proper transforms of lines, and you blow those up, and then you look at proper transforms of planes, and you continue going up in dimension. And the important thing that they noticed is that the corresponding variety, the Chow ring of that is presentation depends only on the combinatorics of the underlying hyperplane arrangement, not on the specific hyperplane arrangement that you picked. And we will see this later. So an example of this is for the hyperplane arrangement I showed you. This would be the blow up along the 4 points that are the flats. And then we could think of blowing up the proper transforms of the lines, but they're already codimension 1, so nothing happens. And the note at the bottom of the previous slide is just that the Chow ring of the wonderful model of this hyperplane arrangement is generated by the classes that I've actually colored in here. So these divisors generate the Chow ring, and the relations are just the product of two divisor classes is 0 if they don't intersect. And there are many ways of writing the pullback of a generic hyperplane, and those should all be the same. The thing that the Concini and Procesi noticed was that this can be encoded in just the combinatorics. So when I say the combinatorics, I mean the matroid associated to this hyperplane arrangement. A matroid, we will see later, is a pair of a set and a rank function. In this case, what we would like to generalize in the concept of a matroid is the rank function that assigns to a subset of hyperplanes the codimension of their intersection. Then the structure of the Chow ring of the wonderful model in terms of this matroid is given by its all integer polynomials, polynomials with integer coefficients on variables x sub f, which are the subsets of hyperplanes, cutting out specific geometric flats of the hyperplane arrangement, modded out by the two relations I mentioned. The product is 0 if the two sets of intersections don't intersect so the blowups over the flats don't intersect after I look at the wonderful model. And there are many ways of writing hyperplane arrangements, and this is the way in which that is encoded by the combinatorics. So here is the matroid associated to the hyperplane arrangement I just showed you, sort of. This is actually what's called the lattice of flats. So in this case, because we're coming from geometry, we have a concept of a flat. There are linear subspaces inside of my P2. And here, the notation is that I've suppressed H sub. So 0 here is supposed to mean H sub 0, the 0th line. And 1, 2, 3 is supposed to be the place where H1, H2, and H3 intersect, aka this point, and the height is given by the codimension of that intersection in P2. So, in general, if you give me a rank function in a finite set on which you've defined this rank function, and your rank function satisfies these three axioms, which I won't go into detail, then you can define similarly a lattice of flats. However, the way in which we came up with our specific example of a matroid, aka we looked at hyperplane arrangements and we assigned the rank function to be codimension of the intersections. Almost all matroids arise not in that way. It is impossible to find a hyperplane arrangement which gives you a specific choice of finite set and rank function for almost all matroids. I believe, what is it? All matroids, the lower bound is something of the order 2 to the 1 over n choose n over 2 minus n log n. And the upper bound for realizable matrix is 2 to the n cubed over 4, which is the result of the paper by the same name, Almost All Matrices Are Non-Realizable, by Nelson. So we shouldn't expect things that work for realizable matrices to work for all matrices because it is a significantly larger class of things. However, we had the concept of a Chow ring that we could assign to realizable matroids, and the presentation for this ring depended only on the matroid itself, not on the fact that we had a geometric object whose Chow ring was this thing. So in 2004, Feigner and Jusvinsky defined the Chow ring for an arbitrary matroid, and then it's become part of the business to see whether a class that you can define in terms of geometric things, such as the CSM class of the complement of a hyperplane arrangement, can be ported into the idea of just associating it to a matroid instead. For this, we generalize the concept of a Chow ring to the concept of the Chow ring of the matroid, but the Chow group is generalized instead by the idea of Minkowski weights on the Bergman fan. I won't talk about the structure of this in detail because it's not really important for the talk, but these are just two different presentations for the same underlying group of the ring that I describe over here. And just like with the case of wonderful models, which are blow-ups of PN in non-singular along non-singular centers, we have Poincare duality even when the matroid is not associated to a hyperplane at all. So in 2019, López de Medrano-Rincón-Shaw saw that actually the CSM class of the complement of a hyperplane arrangement in its wonderful model had a formula that we could write down in a way that depends only on the matroid. So it never looks at geometry. It doesn't know about this functor of constructible functions. It just looks at the information of the matroid and spits out which class as a Minkowski weight it should be. And then there are different ways of translating the information of a Minkowski weight into the information of an element of the Chow group of the wonderful model. And in the same paper, they show that under this equivalence of groups, the CSM cycle of a matroid, when this matroid is realizable by a hyperplane arrangement, corresponds to the CSM class of the hyperplane arrangement, or sorry, the complement of the hyperplane arrangement in its wonderful model, of course. Then the next question is, okay, so we have the class in the Chow group, but when I computed the CSM class of the complement of the union of two lines in P2, I really gave you an element of the Chow ring capped with the fundamental class. So people have been searching for, well, what should the Chow ring element be? In a thesis by Eileen Manino, they reference a conjecture that Tara 5 and Felipe Rincon made about what should the Poincare dual of the CSM cycle of a matroid be in general, and they gave an expanded form for this. So this year, Jeffrey and I realized that using the theorem by Alufi that I mentioned at the beginning, you can get a formula for the realizable case. And so we sat down and proved that the Poincare dual for the CSM cycle of an arbitrary matroid is given by the same formula that geometry predicts.
15
In,
minutes.
okay. In particular, we showed that this formula reproduces the conjecture of 5 and Rincon, so it proves that this is actually a theorem. And the last thing that I want to do is give you a very, very short sketch of the proof because I think it is remarkable how simple of a high-level view it gives you. All we did was we derived the formula for realizable matroids. Then we showed that this formula that we derive for an arbitrary that we define for an arbitrary matroid satisfies a contraction deletion formula, which means that we can take our matroid and decompose it into smaller parts and look at those parts instead and look at the classes of those parts. And then put the information back together to give you the CSM cycle for the original matroid. And then once you have this, because the original CSM cycle, the one defined as a Minkowski weight, also satisfies contraction deletion relations, we just need to do induction on the number of elements of the underlying set. So with this, I finished my talk. So here are my references, and thank you for your attention. And if you have any questions, I guess we have like 4 minutes for that.
Thank you very much. Great talk. Any quick questions?